Bismillahirrahmanirrahim. Welcome to the third part of the 10th lecture of Statistics and Probability Theory. We will continue with the topic Binomial Distribution. An exam consists of 10 multiple choice questions. Each question has 4 possible choices. Only one is correct. Jeff did not study for the exam, so he just guesses at the right answer for each question. He is doing a pure guess, not an educated guess. What is the chance of passing the exam? That is, to make at least 6 correct answers. Now, if you concentrate of the scenario, so you come to know that the Jeff is a guy who did not study for the exam and he is just guessing the right answer for 10 multiple choice questions. You have to find out the chance of passing the exam, and the condition is that he should at least mark 6 correct answers. Now, let us consider that binomial probability distribution function can be applied here. So, if this scenario follows the binomial distribution, it should satisfy the 4 assumptions of the binomial probability distribution. The very first assumption is that each trial is classified into 2 possible outcomes, success and failure. If you concentrate on the scenario, it is saying that what is the chance of passing the exam? He will pass the exam on the basis of the at least 6 correct answers. So whenever he marked the correct answer, it would be the success, and whenever he marked the wrong answer, it would be the failure. So our success is marking the correct answer in 4 possible choices. Second assumption is the experiment is repeated a fixed number of times. Here we have 10 multiple choice questions. So we know that n is equal to 10. Third assumption is probability of success is constant. Here the chance of success is basically marking the correct choice in the multiple choice question. So we have the 4 possible outcomes, number of favorable outcomes divided by total number of outcomes, and chances of correct answer is only 1. So probability of marking the correct answer is 1 by 4, which is 0.25. And Q will be equal to 1 minus P, which will be equal to 0.75. Now the fourth property is the all successive trials are independent. Here the trial is the attempting the question. If Jeff is going to attempt the first question, it would be his first trial. If he going to select the second question or mark the second question, this would be his second trial. So all successive trials are independent. One trial is not affecting the other trial. So all the four properties of the binomial distribution is satisfying this scenario. So we can apply the binomial probability distribution here. As we know that probability of success is 0.25, n is equal to 10, and q is equal to 0.75. Probability of passing an exam, they are saying that he should mark at least 6 correct answers. So at least means that he should mark minimum 6 correct answers. They are only specifying the minimum limit that it should be at least 6. So he will pass the exam if he marks 6 correct answers, or 7 correct answers, or 8 correct answers, or 9, or 10. We can go to the 10 because total number of questions are 10 and it's equal to 10. So this is the probability of passing an exam. If you say probability x is equal to 5, it means that he will mark 5 correct answers. So the condition for passing the exam is at least 6 correct answers. So we can't include here probability x is equal to 5. We should have 6 correct answers at least. So by applying binomial probability distribution function, which is equal to probability x is equal to x is equal to n c x p raised to power x q raised to power n minus x and x is equal to 0. X is basically our variable of interest, which is associated with the probability of success. Here x is equal to 0 means he will mark 0 correct answers. That is, all the 10 questions marked by him will be wrong. X is equal to 1 means he will mark 1 correct answer. X is equal to 2 means he will mark 2 correct answers. So maximum he can go to 10 because there are 10 multiple choice questions. There are 10 trials. So by applying or by substituting the values as n is equal to 10, you can write it in this way also. P is 0.25 raised to power x and q is 0.75 raised to power 10 minus x. So whenever we say probability x is equal to 6, we will substitute here 6. 10c6, 0.25 raised to power 6, 0.75 raised to power 10 minus 6. Whenever we say probability x is equal to 7, we will substitute 7 in the place of x. So by applying this, we will get this thing. 10c6, 10c7, 10c8, 10c9, till 10c10. And the final answer will be 0.01973. So this is the probability that Jeff will pass an exam. As he was making the random choices, that is, he was making the pure guess not on the basis of the education. He did not study for the exam. That's why probability of passing his exam is very low, which is 0.01973. There are very less chances of passing his exam. The probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted this disease, what is the probability that at least 10 survive? From 3 to 8 will survive. Exactly 5 will survive. Now, first of all, we look at the scenario whether it follows the binomial distribution or not. The very first property of the binomial distribution, if you recall it was that there should be two possible outcomes, success and failure. So what is the success for us? We have to find the probability that at least 10 will survive. So you are interested in the number of persons who survive. So your random variable x will associate it with the number of people or number of persons who survive. Number of persons who survive. So this is basically your variable of interest. And you have two possible outcomes. If the person contracted with the disease, there would be two chances that whether he survives the disease or not. So when as you are interested in the number of persons who survive, so your success will be the probability of the patient who recovers from the rare disease, and failure will be that probability of the person who did not or who does not survive or recovers from a blood disease. So here probability of success is P is equal to 0.5, which is given in the very first line of the question, that the probability that a patient recovers from a rare blood disease is 0.4. So according to this, what will be the Q? Q will be 1 minus P, which is obviously 1 minus 0.4, and it will be equal to 0.6. Now, what is the second property, or you can say assumption? The experiment is repeated a fixed number of times. So here we are considering the 15 people. So we will go through the 15 people to check whether they are survived from the disease or not. So we have n is equal to, or number of trials is equal to 15. Now the third property is probability of success remains constant from the trial to trial. Here we have probability of success 0.4, that is the probability that a patient recovers from a rare blood disease. We have 15% persons. If we select the first person to examine, here the probability of recovering is 0.4. For the second person, third person, fourth person, whether the 15%, this probability of recovering will remain the same, that is 0.4. So the third property is satisfying here. The very last assumption or property of the binomial distribution is the successive trials are independent. We have 15 people and each person is independent from the other person as they are contracting with the blood disease. So they are independent. So for each trial, successive trial is independent. All the four assumptions of binomial distributions are satisfying here. So we will apply the binomial distribution. Here P is equal to 0.4, Q is equal to 0.6, N is equal to 15. The very first thing we have to find that at least 10 will survive. We know that PDF of probability mass function of binomial distribution is NCX P raised to power X Q raised to power N minus X, where X is equal to 0, 1 till N. Now by substituting the values, n will be equal to 15, p will be equal to 0.4, q will be equal to 0.6, and we are finding out that at least 10 will survive. So probability x is greater than equal to 10, because they are saying that minimum 10 people will survive. They are not restricting the upper limit, they are just restricting the lower limit, that minimum 10% will survive. So minimum 10%, you will start with probability x is equal to 10 plus probability x is equal to 11, x is equal to 12, till you will go to the x is equal to 15, because you have total 15% here. They are just bounding you to the limit that minimum 10% will survive. So you have to start from the x is equal to 10. By substituting the values, you will get 0.0338, as this is the probability that at least 10% will survive from the rare blood disease. In part B, they are saying from 3 to 8 will survive. So this is the probability that 3 to 8 will survive. So this is x is equal to 3 plus x is equal to 4 plus probability x is equal to 5 till probability x is equal to 8. You have to find the probability that 3 to 8% will survive. So this is the way to find out the probability. By applying the probability mass function, you will get 0.8779, which is the probability that the 3 to 8% will survive. In part C, they are saying that exactly 5 will survive. So we will substitute x is equal to 5. So what we get? We will get 15c5 0.4 raised to power 4 and 0.6 raised to power 15 minus 5, which is equal to 0.1859. This is the probability that exactly 5% will survive. Let me leave you here from the with the question that if you say that exactly 5 will not survive, how to find the probability that exactly 5 will not survive? Just think about this, concentrate on the scenario and think about this, how you will find the probability that exactly 5 will not survive. Now, next example, fair coin was tossed 3 times. What is the mean and standard deviation of number of heads occur in 3 tosses? As you know that tossing a coin is a binomial process, that each trial has two possible outcomes, success and failure. Here we are interested in the number of heads, so success will be number of heads, and probability of success remains constant from trial to trial. Here we are interested in number of heads, so probability of success will be 1 by 2, which remains constant for all trials. Experiment should perform a fixed number of times. Here we are tossing coins 3 times, so n will be equal to 3. Each successive trials are independent. You toss coin 3 times or 4 times or 5 times, each time each outcome will be independent from the other outcome of the other trial. So what will happen here? P will be equal to 0.5, 1 by 2. Obviously then q will also equal to 1 by 2, that is q is equal to 1 minus p, and is equal to 3. We have learned in previous part that mu is equal to n into p. So n is equal to 3, p is equal to 0.5, so mean is equal to 1.5, and sigma, or you can say standard deviation, is equal to n p Q, which is equal to 0.866. This is the way to find out the mean and standard deviation of the binomial distribution.